start us. We first duration. There are two kinds that we have creation. So only difference between them is that creation y will be continuous, while in the classification models, y will be depending on that. We also saw some that tend to in regression y logistic. This case, eh, before we go into basic, basically to come at all. Why there was that with so about the different has to be some problem with the existence. So there was few problems because of coming different. So start with problem logistics. This stated uh, by with the help of a line. LR will give you very good accuracy. Data can line, which is a linear, but the data whichever cannot this database or logistic data like divide, but still your data the one side. This was also red. Then you could have lines right? This red and but as there is a different y in quadrant, you cannot simply kind of separate out this. This is also so basically for any non data logistic regression, whereas for data logistic, so any data that can be divided by simply that data is very good, nicely separated by logistic. But any data which is by logistic regression, here till now, why we need basically start with. Let's so we have a data like decision will uh, quadrant will decision will be separate based on getting the database. The rule, look, Banana, this doesn't work. Similarly, like, yes, based on the similar thing, we will start with, let's say, apply this it is quadrant second, all the point quadrant. So if it is yes, that bucket only quadrant quadrant. If I now see uh, came up with one condition stated four quadrant different. So it is started with condition. So will like currently I'm able to see, so I can come up with these conditions. But whenever we don't see the data, that we will cover. Basically, the process what we did is started with data, define case here people would have again done another question.
Here, we just give the condition and the conditions get operated on the each quadrant.
So each point of the data. So currently I'm just stating the quadrant, but actual data would be each point, each of
Yeah.
these points. So on that each point, the condition will get operated, and based on that, it will get categorized. The condition all the x are red basically. So if I basically apply the criteria that this condition, all my data would be segregated properly. Categories red and blue. So basically, based on the data, we will choose uh, like criteria, like conditions. But uh, like how exactly now I can see the data, so I can like easily choose the condition. Actually, without looking how to choose the condition, that we will see. But uh, is this idea clear? What we are doing
Yes, yes,
for
yes.
each of this data, each of this row, we will apply this condition. Let's take this row. The first row is x is equal to x7. So first it will so my first one is equal to 7. So now it will come to this criteria, is x1 greater than 0. So in this case, answer is yes. It will go here. Then then it will go to the next, is x2 greater than 0. Then here my x2 is 7. So it will it is yes. So it will go in this first. Now
So it
same
is.
for
So,
the,
things we should know. Many conditions we need to operate or some. What is it does.
yeah, so there is a way it chooses the condition. We'll come to that.
Okay.
So there is a method to, very simple method, very straightforward. So there is a way it chooses the condition, and also there is a limit on how many conditions. But is this idea clear what this algorithm tried to do?
Yes.
Simply, it categorizes in the book, just like there is a four balls and have two buckets, what we will do first, we will pick up one. We will ask ourselves, is this blue or red? If it is blue, we will put it in the blue basket. If it is red, we will put it in the red basket. So what we did, took the data, we put a condition if answer was yes to it. So instead of asking if a ball is blue or red, will something like that you will ask if ball is.
Yes.
If answer to that is yes, you will put it in the blue basket. If answer to that is no, then you will put it in the red basket.
Yeah.
Similar thing, this algorithm, for each of the data, it will ask a condition. If answer to that condition is yes, it will put it in the one basket. If answer to that condition is no, it will put it in the another basket. It will continue until and unless you get the pure basket.
Okay.
So before going forward, basket, basket. Which of this is more pure?
Basket two.
So now, why you thought basket?
Yes.
It is correct. I just thought process.
Because the number of balls that are in the same color will be.
So, in majority balls are while only two balls are. But so in order to make it completely pure, you just have to throw these two balls. Have the completely pure bucket. But in case of B1, there is almost uh, sorry, almost 50% are red and 50% are green.
Yeah.
Correct. That's why you said the basket two is pure, basket one. But we'll need to come up with the mathematics for it. For that we will. So first understand with the, let's say, okay. Now what all conditions I can come finding the correct condition. Let us see what all first conditions come up with. So x1 is 1, sorry, equal to 2, x1 equal to 3, 4 equal to less than equal to 6. Can we have this condition less than equal to 7?
Yes.
Will this like help is equal to 7?
No, because all of belongs to.
So as all the data would belong to only one bucket. So this this condition. So what I would say is there are these six valid conditions. Now,
Yeah.
what we need to do is find out the best possible conditions without looking at data. Because right now I can plot the data and I can, but when there are 20 features or 30 features, I can't plot the data and visually see which uh, which condition I should. So what I will be doing is I will come up with a method to basically find out the condition best for the current. Now similarly I can come basically with conditions for you as well. So what will be the conditions?
It's great. So,
Right. All the conditions will be same only.
yeah.
Less than one, two. Here also seven won't come because if we all equal to seven, all the data will be coming into one bucket. There is basically no use of condition. So in the case of x2 also there are six valid conditions. Case of x1 also there are six valid conditions. So now the method to the condition that is best for our so what we need is need to tally data such that our choose the condition um, such that it will separate out the separate out the classes properly. That's our aim. Now let us see how to basically come up with the method to find out the best. So current in this are is there are conditions exactly conditions and want to find out what is the way in which I can come up with the method to find out the best condition. That's our goal. So let us see now. In order to find that out, first we will need to define what is our purity. So, just looked into the and told that bucket 2 is more pure than the bucket 1. So we need to come up with the purity metric, and what we will do is whichever condition giving you more purity, that is the best condition. So before that, let me define. So it is a very met. It is called Gini impurity. Instead of defining purity, they define impurity. Lesser the impurity, better is your condition. So purity is very simple. One minus uh, how many are the balls from the class red divided by the total number of so there are 7 data points. Square of that green balls, total number of data.
What is 4?
4 is the number of red balls, is number of green balls,
But
and
that's
divided
from
by total number of
the
balls.
test your bucket.
For any bucket, one bucket, if I
Oh,
want to calculate, if I want to calculate the impurity of one bucket, I will, what I will do is, I will find out the, uh, I will find out the number of data points. Let us take this example. Now let's say I classified it like this: red together, red together, and all these into different buckets. So let's say this is one bucket and this is another. So in the another bucket, there are two, correct? So this
yes.
is my one bucket, red and three blue. So if I want to find out the Guinea impurity for this, I will say 1 by 5 square by 5 square. Red divided by total and blue divided by total. So whichever is belonging to different class. So instead of red, it can be yes, no, male, female, any classification.
Yeah.
So basically, one class, uh, all the data points belonging to one class divided by total number of data minus all the data points belonging to other class divided by total number of data points. Then can you calculate the Guinea impurity for this?
0.4.
Okay, okay. So you can calculate. Yeah. So 1 5/7 square, 7 square. This is what you did.
Yes.
Correct. I'll just summarize this whole thing,
Yeah.
whatever we did till.
Yes.
So, firstly, we started with decision-based model because there was one problem with logistic. What was the problem? Logistic regression works really well for uh, the data that can be separated by a linear line, but it doesn't work for the non-linear. So any data that can be separated by a line, logistic regression works really well for that data, but it doesn't work well for the data where cannot separate out the data with a line. So then we came up with a model called this. So in decision tree, what we said is we will take our data, okay, then we will pass it through a certain condition. If it satisfy that condition, we will classify it under one bucket. If it doesn't classify doesn't satisfy the condition, we will uh, put it in another bucket. And then in those buckets again we will apply a condition. If it satisfy, we will put it in one bucket. If it doesn't satisfy, we will put it in another, and we will continue it till we get uh, like pure buckets. What so what we said is we will have the data, we will define a condition. Based on the condition, we will segregate the data and we will repeat the process until we get pure. Now, what we said was pure bucket. Pure bucket is where you have the uh, all the data points of a particular uh, type. So what we said is this B2 bucket more pure to B because here there are majority of red data points and very few compared to that of uh, bucket 1. So what our aim is to reduce the impurity. We want to go from the bucket like bucket 1 uh, bucket 2. So we want to go from the higher impurity to the lower impurity. So now in order to like here I can basically see the data and come up with a condition like x1 is greater than 0, 2 is greater than 0. But in actual real life scenario, how do I come up with a condition? So what I said is uh, in order to define in order to find out that what I did is I first like let's suppose this is our data, and what we said is so first write down all the conditions that we can come up with. So in this case I can come up with 6 conditions. These are the only valid conditions. Scratched out the x1 less than equal to 7. That is because this criteria, this condition, basically put all the data points in one bucket. We didn't want that. So we have 6 valid conditions. Now our aim is basically to find out best condition for uh, for our data. So, in order to find out the best condition, what we said is we will define a metric called impurity. We'll call it Guinea impurity. How we will define it? This way. So, one number of data points belonging to class 1 divided by total number of data point. Where of that of data points belonging to class 2 divided total number. Okay. So this is how we will define the name. Any doubt till now? Any doubt till here? Till here? Tabari, be with me. Be clear. Sorry?
Watch it again.
Okay.
Together. Reviews.
Okay. So, yeah. So now our aim is find out the condition out which is having less impurity. This is our aim. Let us just take one the same data. Let's take the condition x1. I got the data. I use the condition on the table. Let's say I use less than equal. Now, what would be my? Just tell me the color I will have in number of red balls and number.
One red, one blue.
So in this case, how many have? One red, right? Now in this bucket, how many?
We have three red.
Correct.
Yes.
In this case, I had three red, three blue. So now, when I started with the table, I had how many? Four red.
Three blue.
So first, let us calculate the impurity for this. This is the impurity. 1 minus 4 by 7 square minus 3 by 7 square. So, uh, red balls divided by total balls, my square of that. Blue balls divided by total number of balls. Right?
Yeah.
4 by 7, 3 by 7. So this was my initial impurity. So call this initial impurity. So, so now the this bucket is completely pure, so the impurities we will see mathematically also. So if you calculate it mathematically, then also it will see how many red are there. One red out of total number of one. How many blue are there? Right?
Yeah.
Still one minus impurity for this. Calculate the impurity for this.
So which one? Sorry.
For this bucket.
Okay.
Second bucket.
Zero point 0.5.
Minus square. One minus of square will be minus one. Can you calculate? Can you calculate how much this number?
Zero point 0.49.
4 9. To the impurity. Calculate the score. How I will calculate initial impurity. Do I calculate to calculate the fine? I need to sum this, but I cannot take the direct sum because I need to take the weighted sum because in each bucket there are different number of data. So the final impurity will be there are total so there are total how many data points? 7 data points. Out of that 7, one is the first bucket. The Skinny impurity that we calculated for the first bucket is plus second bucket. So in the second bucket, how many data points we have? 6 divided by 7 into uh, the impurity that we get 0. Initial impurities and final impurity is plus by 7 into 0 by 7 by 7 point out to be 0.42. Four be 0. So this is the score. So more the score, better is your condition. Clear? How we calculate it?
Yes.
Can you do the same thing?
No, no.
Can you calculate it now for the condition 1 less than equal to 2? So see, initial impurity is gonna be same 0.49. This is not gonna change. So the initially table initially there are uh, four data points. So initial impurity is gonna be 0.4 impurity 4. Now condition x less than equal. For this condition, as from the table, if it's yes, what is the bucket? If it's no, what is the bucket? So how many red, how many blue? And based on that, calculate the impurity, initial impurity and final impurity. Tell me what is the number that you got. Question is clear, right?
Yes.
Okay, so let us solve it. So, for the table, so what is the final value that you got? Mine. Final, yeah, score is fine. Okay, correct. It is. The score is correct. We'll just solve it once. So, if x1 is less than equal to 2, okay, x1 is less than equal to 2, then these two data points will fall in one bucket, all other will fall in another bucket. Okay, so the bucket I have is 2 red for yes, and for no there are 2 red and 3 blue. Correct. So now what I will do is I will calculate the impurity for this, which is 1 minus 2 by 2 square minus 0 by 2 square. Okay. So this comes out to be 0 because it is and it makes sense because it's pure, so value will be 0, impurity will be 0. Okay. Now for this one, 1 minus 2 by 5 square minus 3 by 5 square. So, it comes out to be 1 minus 4 by 25 minus 9 by 25. So 25 minus 4 minus 9 divided by 25. So it is equal to 12 by 25. Okay. So this is my impurity for the bucket 2. So the total final impurity is equals to, there are total 7 balls or data points that we have. Out of that, 2 are in first bucket. So 2 by 7 into the impurity of the first bucket, which is 0, plus 5 by 7 into impurity of the second bucket, which is 12 by 25. So this comes out to be 12 by 35. So the final impurity is equal to 0.342. So this value comes out to be 0.342. So the score, sorry, score is equals to initial impurity, which was 0.49, right? This is where we started, 0.49. Okay. And then the final impurity is 0.342. Okay. So then it is equals to 0.1477. Now you can see, right, the score is improved. Like first the score was 0.07 for the condition 1. For the condition 2, the score is 0.1477. So it is improved, correct, from the first to the second. Now can you, now visually if you see, the best condition is this condition, x1 is less than equal to 4, right? Can you calculate the impurity for that, score for that? 1 less than equal to 4. Correct. Because all the impurity will be 0. So let us see. Initially there were 4 blue. Sorry, 3 blue, 4 red. Right? Now we use the condition x1 less than equal to 4. So one bucket will be there with all red, another bucket will be there with all blue. Correct? And then so for this, yes and no means satisfied and not satisfied. So the impurity for this will be 0, impurity for this will be 0. So the total final impurity will be 0. So therefore score will be equal to 0.49 minus 0, which is 0. Which is the highest score that you will get. And then again the score will go on decreasing. You can try for this one, but anyways, so even if you try for this, again the score will decrease. We can quickly try actually. So for so this was our initial blue, 4 red. Okay. Now our condition is that x1 is then equal to 5. Now can you tell me what will be the first bucket? Yeah. Sorry, less than equal to 5.
4R.
Okay. 4R and 1 blue. Now you can see here itself, we are going from the pure bucket to impure bucket.
Yes.
And then remaining 2 blue will be here. Impurity for this will be 0. Right? Any impurity for this will be 0. For this, the impurity will be 1 minus 1 by 6. 6 no, 5. 5 square minus 4 by 5 square. Okay. So you subtract this 9 minus how many other 1 2 3 4 5. So 5 by 7 into whatever this value is, but still you are subtracting a non-zero number from 0.49, so it would be definitely less than 0.49. So how much this number comes to be? 1 minus 25 minus 10, 25 minus 16 minus 1 divided by 20. So how much it is? 8 by 25. Yeah. So only for the best condition you will get the higher score. Okay. For anything other than that, you will get a lesser score. Correct? Understood? So this is the way you will find out what is the best score that you can. Okay. So so this is how you will select the condition. So you remember you had asked another question. So how many times we will go on segregating this? That was your another question, right? So we will answer that now. So let's say we start with this bucket where there are 4 blue and let's say 4 red. Okay? And let us say we did segregate it like this. Okay, so instead of having all the pure buckets, we have something like this. Uh, Red, and I have 2 blue, and then maybe 2, 3 red, and 2 blue, something like this. Okay. Now, what I should do after this? Let's say this is my for after the first iteration, I got this. What should I do now? I should again segregate the second bucket, right?
Yes.
So if I segregate the second bucket, let's say I got something like this. One blue and then one blue, one red. Okay. This also I segregated and I got let's say uh one red, one blue, um one red, and then how many things are left? Two red and one blue. Let's say I got these values. Now again I would go on segregating this part, right? So one blue, one red, then again one red, one blue, and again I will do same thing here maybe. Okay. So these are the final buckets that I have. This one and all these. Correct. But now if you see, majority of the data is classified in the separate bucket. So if I have 7 data points and I have 7 buckets, doesn't make sense, right? So you have classified basically each data into separate class. Correct. So this doesn't make sense. So that is why how many times you can continue like this, we have made a rule. So how many times you can segregate the data based on the condition, we have a certain rules for that. Okay. So the first rule is, so when should we basically stop? When should I stop? Should I stop here? Should I stop here? Or should I stop here? At which stage I should stop? So in order to define that, we have basically we have three conditions. The first is if bucket is already pure, don't split. So for example, in this case, okay, so there are 2 red, bucket is already pure. I shouldn't separate it into split it into another 2 buckets of the red. Correct? Even in the previous case, I can show you. So for example, here, okay, in this case, I shouldn't separate out this bucket and this bucket into 2 more buckets. Okay. So once it's pure, that means all the definition of pure is all data belonging to the single class, then don't split it anymore. Clear this condition? It's kind of obvious condition. Then the second condition is that if you have very few data points in the bucket, don't split. If very few data points in bucket, don't split. Now, what is the definition? Then you will ask, what is the definition for the few data points? So, minimum you should have 5 data points to split. Okay. If you have anything less than 5 data points, don't split it anymore. So basically here I should have stopped at this place itself. I shouldn't split it anymore because our data points are already less than 5 or almost like it should be more than 5, then you should split. Otherwise, stop it at that point. Clear? Second condition is clear. And then third and last condition, that don't grow a tree beyond height equals to 10. So in this, take this tree. Okay, this is one height. This is the second height. Second, this is the third branch. So basically, the height of this tree is 3 because we have segregated it 3 times. Okay, so like that, don't grow a tree beyond height 10. Okay, so see, if I grow a let me say this was the data. If I split it into 2, from one segregation, I have 2 branches, right, or 2 leaves. Again, if I classify it into 2, so one branch here, one branch here, one here, one here. So now I have 4. If again I classify, I have how many? 1, 2, 3, 5, 6, 7, 8. 8. So you can see here your branches will grow as 2 raised to n, where n is the uh, basically the height of the tree. So if we are saying is, don't grow it up to more than height 10, because by then already you have 2 raised to 10 buckets, 2 raised to 10 branches. So that way you have classified in a lot of buckets. So beyond that, it is not advisable. Clear? Clear or not? So till now, any doubt you guys have? Any doubt till now in the decision tree? So the theory of decision tree is only this. There is nothing else to it. But we will now see the random forest and bagging. So, but before going to that, is there any doubt in here, like in this? Okay. Okay, then what we will do is we will take 10-minute breaks. Currently it's 9:36. We will meet at 9:45 and then we will start with the concept of random forest and tagging. Okay. So then let's meet at 9:45. Decision tree, right? All the things are clear. So now, if this is clear, then understanding bagging and boosting won't be very difficult. So, uh, the concept of bagging is like this. So, before understanding what is bagging and boosting, let us first understand what is the problem with decision tree. Only if there is a problem, we should look for the solution. Otherwise, we can continue with the current. So, first problem with the decision tree. So, the first problem is that you it over learning. So it overlearns the data. That means you will get high training accuracy, like many times you will also get something like 100%. Okay, so the training accuracy would be around 100%. But when you are testing, the accuracy would be very bad, like 60% or 70%, like that. So the training accuracy will be very high, testing accuracy will be very less. This is uh, this is what happens when the model is overlearning the data. Okay, so this is one problem with the decision tree. So the second problem is of inconsistency. So let's say there is a group of there is a group of 10 people. Okay, and to them I gave the same data. So I gave one data to all the people in the group of 10. Okay. Now what they did is they split the data into uh, training and testing. So all those 10 people split the data into training and testing. Okay. So all those people split the data into training and testing. Now, though the data given is same for all, training and testing data would be different for each individual because they are choosing it randomly. So for example, out of the 1,000 samples, let's say there are 1,000 rows. Out of that, 800 you are choosing for the training, 200 you are choosing for the testing. But which 800 you will choose, you are choosing it randomly, correct? So the train and test data will slightly differ for each individual. Okay. Now, as the training and testing data is different, everyone will, let's say, everyone has built decision, sorry, not DF, DT, decision tree. So let's say each one of them has built a decision tree. Okay. So for so what will happen is one person might get very good test results. So training is not a problem. Most of them will get 100% accuracy for the training data. Okay? But while testing, one person might get a result like 80%, while another will get testing result like 60%. So the data was same, the model that they built, like the algorithm was the same, but one is getting 60% accuracy and another is getting 80% accuracy. So this kind of inconsistency is common for the decision tree. So for the testing data, you will see the accuracy ranging between 60% to 80%. So so for the same data, we are getting much uh, vastly different results. Okay, so the problem is clear why we want to go or improve basically the decision tree algorithm. Clear? So now there are two ways to resolve this issue. One of that is the random forest, and second is bagging. Let us see the bagging first. Bagging stands for bootstrap aggregating. Okay. This is what bagging stands. So let us let us first I understand the philosophy behind it. So first, you remember like when we used to do all the experiments in the when we are in the school or college. So let's take one physics experiment example. If you remember the pendulum example, when you do the experiment, you just don't do the uh, experiment once. You do it multiple times, right? So experiment 1, experiment 2, experiment 3, and so on. Let's say 10 times you repeated the experiment. And what you submit is not the individual results, but the average of all these. Average of all these experiments, right? So instead of submitting the individual value, what do you submit is aggregate value. And as we have seen previously as well, when we aggregate, the error and or the variation also decreases, right, by the factor of 1 by n. So you can have some water and you're fine. Yeah, yeah. अभी मौसम भी थोड़ा. So when we average out the experiments, then there is a obvious like uh, the error is reduced, and uh, when we submit the aggregate values, uh, we get better results basically. So instead of submitting individual values, we submit the aggregate values. So similar thing we will be doing in the case of decision tree. So we will create, instead of creating one decision tree, we will create 10 decision trees. Okay. And we will average out so how to average, we will see that. But what we will be doing is, instead of giving the data from the individual tree, what we will do is we will average out, and then we will give the results of that average, whatever we got from the average values. Okay. So this is what the concept of bagging is. Instead of giving the prediction from single decision tree, what we will be doing is we will constructing 10 decision trees, 10 independent decision trees, and we will aggregating the data from those 10 decision trees, and then we will give the prediction. Clear? Okay. Now let us see how to first construct the 10 independent decision trees. So, so we want to construct independent decision tree, right? Now, in order to construct independent decision tree, we first need to have the independent data first. So we want independent data set. Okay. So what our goal is, like what we said is, instead of giving the prediction from one decision tree, what we should do is we should construct 10 or 100 or any number of like independent decision trees, and then instead of giving independent individual decision tree value, what we will do is we will aggregate all those decision tree predictions, and then we will give the output prediction. Clear? So instead of giving the output from one independent decision tree, we will aggregate the output from all, and then we will give the prediction. So now we are now faced with another problem, that in order to construct 10 independent decision trees, I need 10 independent data sets. Now I can't go and ask my customer to give me that I want to construct 10 decision trees, so give me 10 independent data sets. I can't go and do that. So whatever data that we have, from that only we need to construct 10 individual independent data sets. Okay? It is not that straightforward problem to, because it's actually a difficult problem. So there are two ways basically to go about it. So let's see that. So let's say I have data. Okay. First, I will divide the data into train and test. Now this testing data, keep it aside. Don't touch it. Okay. Keep this data aside. Don't touch it. So this part you keep it separated. This part is separate. So you don't do anything with this data, testing data. Now only thing that you are left with is this training data. Correct? Okay. Now this training data we need to use to create 10 data sets, independent data set. Okay. Now let us say that this training data has features like x1, x2, y, and let's say the shape of this data is 1000 rows, 3 columns. Now out of this data, I need to construct 10 different decision trees, and for that I need 10 different data sets. So I need now 10 different data sets to be constructed from this training data. Here, now how do we divide 1000 rows? So can you think of, so I should divide 1000 rows into 10 data sets, or from the 1000 rows I should construct 10 data sets. Can you think of any example, any way of doing it? One thousand rows I have, and I need to construct 10 data sets from it. Yeah, so one way to do it is first divide the data equally, so 100 rows each. Correct? So you have 10 data sets, so 100 into 3, and you have 10 data sets like that. Correct? And for each data set, you will randomly select the values. Correct? But do you see any problem in this process? Mhm. Not really, because you have randomly chose the data set, correct? One data point is not dependent on the other one. So it is independent. That is fine. But do you see there is very less data? So basically, if I need to construct, let's say, 20 decision trees, you will have only 50 data points. So other than having very less data, there is no problem with this method. But the data is very less. So even if you make 10 decision trees, the decision tree made with weak data set will be weak model. Okay, so with less data set, you will make a weak model, and even if you aggregate the data, aggregate the 10 decision tree, the aggregation of all those weak decision tree won't be so strong. You will have weak model at the end. Correct? So now the problem with this is that dividing it this way is that um, I will have less data, so my model will be weak. Now I want the data to be more, but I also want uh, the model to be strong. So can you think of any other way? Okay. So there are two types of sampling. Okay? There are two types of sampling. One is simple random sampling with replacement. This is with replacement. And one is simple random sampling without replacement. Okay, one is with replacement, one is without replacement. So let us say in the bucket I have 3 balls, 1, 2 and 3. Okay, now of if I take it without replacement, I will have only 3 combinations. I can pick one ball first this ball, and then second this ball, then 1 and 3, 2 and 3. Okay. If I chose 2 balls at the random, I can have only these 3 possibilities for without replacement. Okay. But with replacement, along with this, I have few more possibilities. These possibilities will be there. But along with this, I will have few more. Can you tell me which are those? No. What I mean is, okay. You are saying 2, 1. Okay, that is also possible. But what I mean is, this is also possible. Correct? Yeah, what you said is also correct. 2, 1, all those will also be there. But let's say, like, okay, let me say it like this: red, blue, and green. Okay, if balls are like this, then if you chose two at random, okay, then you can have one red ball, one blue ball, one blue ball, one green ball. It doesn't matter the which one you got when. I mean, this is same as getting blue ball first and red ball second. In any case, you will have one blue, one red, one blue, one green, one red, one green, both red, both blue, and both green. Okay. So this is with replacement, this is without replacement. Okay. Now what we do in case of bagging is, say we have this data set. We already removed the test part. Okay. So this is the training data set that we have. It has 1000 rows. So now what we do is, when we are taking the data set out of this, what you showed here is example of without replacement. Okay, like you are just taking out 100 rows. Now you are left with 900. You will again select out of those, again 100 out of those 900, and so on. You will continue like that. Correct? But here what we will be doing is, we will do it with replacement. So what I mean is, we will have first 1000 uh, rows, right? 1000 rows, 3 columns. Let's say this is my data, E7, 100, something like that. Okay, let's say this is my data. Okay, now first what I will do is, I will select first row. This is next to y. First row randomly from this 1000. Okay, let's say the first row that I selected was this. Okay, now again I will select the second row out of the 1000 only, not out of 900. Okay, again I will choose one row out of this 1000. So maybe the second row I will get is this. Now third row, again I will select out of the 1000. So maybe the first row will be repeated, but that's okay. Okay, whatever you choose at the random, again each time you choose from the same 1000, but choose it at the randomly you choose, and it is with replacement. And this way we can retain up to 80% of the original data. So 80%. So out of the 1000 rows, you select 800 rows randomly. Each time you choose one row, and like that you can make 800 rows. So from 1000 you went to 800 rows. but that is not too much loss of the data compared to what we had, like which was 100. Going from 1000 to 100 was considerable loss of data, whereas going from 1000 to 800 is not, like you retain 80% of the data, which is good. Okay, so this way data will be independent and we will also have good amount of data. Clear? So okay, so now let's say we made 10 decision trees. Now we now saw how to basically come up with an independent data set. We now, once you come up with the independent data set, just now you will make the 10 trees. That's all. Okay. So 10 independent data sets, you will make 10 decision trees and so on. Now, how do we aggregate these decision trees? That is the second point that we will need to see. So how do we aggregate this point? So let's say there are 10 people, okay? You have 10 destinations. Let's say one is Goa and one is Pondicherry. Okay? You need to decide which trip you want to go to. So what do you do basically? So 10 people are there, you have two destinations, you need to choose one. How do you usually choose it? Correct. So what you do is take a vote. If let's say 8 people are vouching for Goa, then you will go to Goa. Otherwise, if 8 people are going for Pondicherry, you will go to Pondicherry. Correct? So such decisions you take based on a vote. Same thing you are gonna do here. So let's say you are making a model to predict if person has diabetes. Okay? So if this is a person, you send it to the first decision tree. If let's say the first decision tree said this person has diabetes, okay, you send it to the second decision tree. Let's say the second decision tree also said it has diabetes. You send it to the third decision tree. Let's say the third decision tree said no, it doesn't have diabetes. Like that, for each up to the 10th decision tree, see what each decision tree is predicting. Okay, so let's say out of these 10 decision trees, 8 of them said yes, the person has diabetes, and only 2 said no, the person doesn't have diabetes. Then your prediction will be yes, the person. Clear? What you will do is take a vote and then you will decide. That's all it is to it. So this is the theory of bagging. Any question till now? Because if bagging is clear, random forest is very straightforward. Uh-huh. Data set. So yes, so once you create, so first you had 1,000 rows and 3 columns. This was your data set. Okay. Out of that, you will create 10 different data sets of 800 rows and 3 columns. Okay, and so on. Okay. Now on each of these, from each of these you will create a tree. What is the method of creating tree? Take that data, apply the conditions on it, and then repeat it until you get the pure buckets, and that's your tree. Yeah. So like that. Mhm. Yeah. So you will first, your goal is, so you first wanted 10 decision trees. Okay. But you use the same data, same training data for 10 decision trees. You will get that same training, same decision tree. It's like saying this. Okay. If I want to do physics experiments, you want to do 10 experiments. Okay. That doesn't mean whatever you got for the first experiment, you write all that data for the all the experiments. That is not what we meant. Means, let's say you wanted to do 10 experiments, 10 experiment values you want. Okay. Let's say from the experiment one you got value 1.7. Okay. That repeating the experiment 10 number of times doesn't mean for E2 also you write 1.7, for E3 also you write 1.7. This is not what we mean. Correct? What we mean is conduct the experiment again for the second time. Conduct the experiment again for the third time. Like that, do it 10 times. Whatever results you get each time, take the average of those. Similarly, if I have a data, 1000 rows, 3 columns, okay. If I if I make decision tree out of this, each number of time I'll get the same decision tree. That is not what I want to do. I want to create 10 independent decision trees. Correct? So that is why what we do is we first create 10 independent data sets. So first we create 10 independent data set. How we do that? We do that with replacement. So this is the method. So you will choose row 1 from the 1000 rows randomly. Then you will choose the second row randomly from the entire data set of 1000 rows. Like this, you will uh, select up to 80% of the data. Okay. Now you have, like that, you will create 10 different data sets. Out of each data set, you create a decision tree. Okay. And 1, 2, 3, and so on. Okay. Now take the vote out of all these decision tree to make the prediction. Is this clear? If you go through it once, if you have doubt, you can ask. Like, So now, if this is clear, then random forest is will be very okay. So, firstly, what is a forest? You understand by the word forest. Forest is something which has trees, all of different height and like very random, right? Like different height, different variety from each other. It's not organized. It's not the same tree or the same height, same length, nothing like that. Correct? That's a forest. So basically, um, a forest is something that has variety of trees, different height, different uh, variety, and so on. So why we first went to the random forest? There is one problem with bagging. Can you think of the problem here in the bagging algorithm? No, no, the data is independent because every time you are choosing at random, so data would be independent, more or less. Yeah. I mean, there won't be any dependency in the data. So that is fine. Do you think it will be a lot of time consuming? Because you are uh, now only 1,000 rows are there, but in actual data set you will have much more rows. You are considering all those, like 80% of that data, constructing 10 trees, and for each tree you are like training the model, right? So the actual so bagging is very time consuming. So random forest, what it tried to do is it tried to make it more time efficient, more efficient and more random. So in bagging, all trees have same features. So in random forest, what they did is, like you saw it here, right? Like we were choosing the rows without replacement, right? So now in the random forest, what they did is, this was the data. Okay. So let me say once. So in random forest, what they did is, just let's say I have 20 each rows like this. Let's say I have 20 columns. This is why. So this data is 1,000 rows, 20 columns. Okay. Now in bagging, what we were doing is we were considering all the columns and we were selecting the rows at random. Correct? Right? In the bagging, what we did was we took all the columns from x1 to x20, but only rows we were selecting randomly, and like each time we will select one row, 2 1 7, so on up to, okay, and each time we will be selecting rows. So first row is, let's say, this was selected, then second row this selected, third row may be repeated, the first row is repeated. So like that we were choosing at random, but we were considering all the features, correct? Now in case of random forest, what we will do is we will also select the features. So let's say now for each tree that you are constructing, you are considering any 3 features. So I will just select any 3 features along with y. So earlier we were selecting rows. Now we will also select the only rows we were selecting. Now we will select the columns too. So uh, yeah, we will be choosing, correct. So how many columns you will have in each tree is up to you. You can have 3, you can have 4. So that is a hyperparameter. Okay. But what now you are doing is you are choosing the number of columns too. Okay. And like this you will construct, sorry. Okay. Like this you will construct the decision trees and then you will average out. So only change from bagging to random forest is in bagging you were just choosing the rows. In random forest you will also choose the features or columns. Clear? So let me just write it side by side, make it more clear. This is bagging and this is random forest. In bagging we first select data with a simple random sampling with replacement. Remember, with replacement process. Then we create a decision tree with the selected data. Correct? And then, haha, So first, in case of bagging, what we did is we first selected the data with replacement, okay, and we retained up to 80% of the data, correct? Then we created the decision tree for that particular selected data. Then we will repeat uh, mm, we will repeat step 1 and 2. Let's say you want to create 100 trees, then repeat it 100 times. If you want 10 trees, then repeat it 10 times. This part is clear, the bagging. Okay. Now for the random forest, what is the process is? First, select the features randomly. Okay. First, you select the features randomly. Now, let's say you, in this example, you selected 4 features. Let's say you selected 4 features for this particular example. Now, create data using the same method, simple random sampling with replacement, okay, for these 4 features and y variable. Okay, then the third step is create decision tree using the above selected data. And then you repeat. No, it depends on you. Like you can select 3. In this case, I'm just assuming it is 4. You can even select 5, 6, 7 more features also you can, or less also you can select 2, 3. It totally depends on the developer. Then repeat 10 times. Step 1, 2, 3. Clear? Only this step is added. Everything else is same. Clear? That is all for the random forest and so decision tree, bagging, and random forest. Any doubt till now? Okay. No question, right? So in this, features are usually selected without replacement, and rows. Usually we select features without replacement, but you can select with replacement as well. It depends on the, yeah, rows are always with replacement. No doubt till now, right? I think we will stop here because a lot of theory today. So, hmm. So what we will do is tomorrow we will. So there are small concepts left in this tree based algorithms. So one is boosting, and then I boosting, and then I have a uh, small concept called L1 and L2. They're very simple, small concepts. So what we can do is tomorrow we will cover these two, and along with that we will also cover the coding part for everything. So okay, let's meet tomorrow then. Even if we start, we won't be able to. So small concepts are there. Huh. Mahesh? Yeah, he has flight tomorrow. Yeah, yeah. He put the post of uh, food